me start by mentioning my co-authors. So this is joint work with Emma Arends and Jos-Peter Katun from RVTH Aachen, Germany, and Marius Bosga from Verimac, Grenoble, France. And our work is about building a framework for the verification of reconfigurable distributed systems. But let me first introduce reconfiguration informally. So imagine we have a large distributed system consisting of nodes or processes that run on isolated computers and that communicate over a network. So in this case, we could imagine a cloud database in which the rightmost part of the figure represent database nodes that contain information, and they are organized hierarchically in grapes. And the left part consists of server nodes that handle connections from outside clients to the database. They relay these connections. And reconfiguration in these systems such systems can occur in several cases. For instance, one process dies, faults, and then the traffic has to be redirected to another node. Or for instance, we can have a node that is overloaded by too many connections, and then we have to supply further nodes to handle the traffic. Or simply inside the database, we could have a certain node that starts getting lots of requests at a certain point, and then it is convenient to move this node from the inside of the grape towards the root of the grape in order to minimize internal traffic in the database. And all these kind of scenarios are nowadays implemented in data centers as reconfiguration programs. So these data centers, they actually have the ability of internally taking the decision and reconfiguring themselves. But what can happen wrong with these programs, with these reconfiguration programs? So to understand, let's consider the situation where we have a token ring protocol in which the components are two state machines. One state called token indicates the presence of a token in the node, in the process, and the whole state indicates the absence of the token. There are transitions from whole to token called in, and from token to whole called out. And these transitions are synchronized over the network via edges between these processes. We call these edges interactions. So for instance, executing an out-in interaction between two nodes in the network results in a joint execution of the two transitions attached to the interaction. And that means that the two nodes have changed their states at the same time. And this simulates the passage of the token from node X to node Y, and then it can go on to the right. But now assume that there is a reconfiguration program that has a global view of the network, so that can sit in a specialized reconfiguration manager or network manager. And this program chooses at some point to disconnect the interaction between the token node and the node to the right of it, and then to disconnect the interaction to the left of it, then remove the token and reconnect the remaining nodes. Well, in this case, the system has no more token to run and ends in the deadlock. So basically, a deadlock means that no interaction can fire, and that is a situation that we do not like very much in a data center to happen. So the whole point is, how do we ensure that such things do not happen, and how do we ensure that our reconfiguration programs are correct? We do this by providing three ingredients. Essentially, we have an assertion language that describes infinite sets of configurations of the systems. This assertion language is based on separation logic. And then we use this logic inside the Hoare-style program calculus for reasoning and proving correctness of reconfiguration programs. And these proofs, they need some invariance properties that are proved separately by an inductive calculus. And this inductive calculus also uses separation logic. And this is like the global scheme of our framework. But first, let's understand what are configurations. Simply, a configuration is a network consisting of processes and interactions together with a snapshot of the states, of the local states of each component. Yeah, so here we have three processes, three components. The first one is in state token, the other ones are in state whole, and there are some interactions between them. And this is what we call a configuration. Now we have a logic that describes infinite sets of such configurations, and the logic has an atomic proposition that describes just the empty network, and then an atomic proposition describing a single component in a certain state and no interactions at all, and then another atomic proposition that describes a single interaction and no components at all. And now to describe networks, we use an operator called star, which is classical in separation logic, and that simply describes the union of disjoint networks. So for instance, the configuration before, consisting of three components, three interactions, is described by a formula in which we use an atom for each component and interaction, and then we join these atoms via stars. And on top of that, we can also have existential quantifiers and so on. But now let's see how can we describe unbounded networks. So basically networks whose size is not fixed a priori, but they share a certain architectural style. So for instance, if we want to describe rings, token rings, we can reason inductively. So we can say a ring is a chain together with an interaction from the end of the chain towards the beginning of the chain. And this is one formula, and that is also one inductive rule for the ring predicate. But now what is a chain? Well, a chain inductively, it's one component together with an interaction to the rest of the chain, which is disjoint from it. And this is another inductive definition by another logical formula. You see that we can also label these predicates with some numbers here, H and T, that indicate the least number of components in state whole and state token respectively. And then we can refine a bit our specification to mention these states as well. So for instance, when we write ring 1, 1, that means that we have a ring of unbounded size, but in which there is at least one whole and at least one token. And to describe now reconfiguration by programs, we have introduced a very small programming language consisting of 4 primitives. 2 for creating and deleting components, and another 2 for creating and deleting interactions, this connect and disconnect. Then we have a conditional statement that matches a formula with free variables against the network, against the configuration. And if the formula matches somewhere in some part of the network, the free variables gets instantiated to the components where that matches. And then the body of the conditional is executed in interleaving with the interactions. Yeah, and we can combine also these primitives and conditionals with sequential composition, iteration, and non-deterministic choice. So we have a full programming language now. So let's go back now to the token ring node removal and do it correctly this time. So imagine now that our reconfiguration program matches now the network against a formula that says there is a component in state whole, and there is an interaction to the left and one to the right of it. And these X, Y, Z are just placed on these 3 components, where Y is the central component in state whole. And then the first step, only the first step is atomic, and this will disconnect now the left interaction of Y. Then we disconnect the right one, we remove the component and reconnect X and Z. And now, because we have done things in the right order, even though this is done in interleaving with remaining possible interactions in the system, we can prove the following thing. And we can prove that if we have started in a ring with at least 1 token and at least 2 holes, we get back to a ring with at least 1 hole and at least 1 token. And this is the kind of things that we want to prove in our reconfiguration programs. So to do that, we introduce a Hoare-style calculus based on local reasoning. Local reasoning specifies the primitive operations just by involving those resources that are necessary to avoid faulting. So these local specifications only talk about the nodes and the interactions that are needed by these primitives. So for instance, new doesn't need anything. Delete, however, needs a certain component to be present there, and the same with connect and disconnect. Now, these local specifications or local axioms, also called, are used in a global context by the frame rule, and this frame rule simply allows to deduce a Hoare triple from a local specification by joining a frame to both its pre and post condition. This is classical in separation logic, and this also applies only to what are called local programs. Now, unfortunately, the bad news is that not all programs in the configuration language are local, and essentially we can prove that the primitive ones are local, and non-deterministic choices, for instance, and conditionals are local when they do not check for the presence of certain resources. However, sequential composition is not local. And why is that? So let's have a look at the classical sequential composition rule in Hoare logic, which uses an intermediate assertion theta that describes the end, the post condition of the first command and the precondition of the second. Now the problem is that our reconfiguration programs, although sequential, they run in interleaving with interactions, and this requires the intermediate assertion to be invariant under firing interactions. So this is what we have named Havoc invariance, because it should stay the same no matter what havoc those interactions can cause. And a bit more formally, we can say that the formula is Havoc invariant then if by taking any model of it, which is a configuration, and firing any possible state change, we get into another configuration, which is again a model of this formula. And this Havoc invariance now needs to be added as a side condition to the sequential composition rule. Now back to the proof. How can this work? We start from the precondition, we unfold the definition of ring once, then get past the guard of the conditional using a rule which can be found in the paper. And from now on, we can start applying the frame rule by matching the precondition against the frame in red and the local precondition, then applying a local axiom. Again, we match a frame in red and the precondition for the second local axiom, go on like this, generate our proof, and finalize it by applying just this frame rule 4 times. However, the proof we have, it's not completely done yet, and it's not necessarily sound unless we have proved Havoc invariance for those intermediate assertions here. How to prove Havoc invariance? Now, this is a matter of using another proof system, which uses special triples that differ from the Hoare triples just by the fact that in the middle we don't have a programming language, we don't have a program. We have an extended regular expressions that describes a language of interaction sequences. And this is a bit technical, and the details are in the paper. The idea is that we could reduce the Havoc invariance problem to a sufficient condition on the validity of these Havoc triples. And we have a soundness theorem here. And then we prove those Havoc triples by using inductive cyclic proofs. And these are proofs that in which the proof tree is generated by applying rules. And at the bottom of the tree, at the leaf of the tree, either we have an axiom or we have a Hoare triple, we have a Havoc triple that is matched with the previous one by a substitution of variables. In this case, we add the backlink. And the soundness for this proof requires that on this cycle between nodes of a backlink, there is at least one unfolding rule, and then that there is a principle of infinite descent that was stated in the 17th century by a French mathematician Fermat, and which states that these proofs are sound whenever we cannot decrease infinitely these cycles. In conclusion, I have presented a simplified model for dynamic reconfigurable systems, a research logic based on separation logic that describes infinite sets of configurations, two proof systems, one for reconfiguration programs and one inductive system for proving Havoc invariance. And let me conclude with a few references of work regarding the automatic proof generation that has been done since the paper was written. And so that concludes my talk. Thank you very much.
So one question for Radu. So here's a questions from Sophia. First of all, she thanks you for the interesting work. Yes. And the first question is that, do you really on the reconfiguration manager being a global program? If yes, then how realistic is that in the distributed setting? And okay, so can you
thanks for the question. So actually, we came up with this. We looked at some surveys on the reconfiguration languages used as architecture description languages. So in the community of ADL, software engineering that deals with architectures and composition and so on, there are about over 100 languages to describe reconfigurations, a reconfiguration in a component-based system, and there are a few surveys on those languages, and in fact, what came out was that in all of these languages, the reconfiguration it's like global and centralized, and this is just for simplicity. I mean, when people program reconfiguration, doing it in a distributed setting seems to be already quite hard to program, and we adopted this this setting also for simplicity in our framework. Nevertheless, in real life, and there are other papers that we've been looking at that are referenced in our paper. About realistic data centers, and in realistic data centers there is distributed reconfiguration based on clustering, and the idea is that the processes will decide upon some clusters, and then these clusters will be disjoint, and the reconfiguration will happen in parallel within the clusters. And this is clearly a matter of future work for us. I mean, it would be very interesting to do it to do a distributed reconfiguration, but of course would require some extensions to the framework. And we believe this is possible by looking at concurrent separation logics and how concurrent separation logics deal with concurrent programs. We could apply some of their ideas in dealing with distributed reconfiguration.
I see. And next question is can you deal with failure, node failure? If not, can it be extended?
Yeah, so failure in this case would be just moving towards a halting state or an error state within the state machines that model the components, the processes. They are all finite state machines, and adding an error state does not harm. So from the model point of view, this can be done. Then from the verification point of view, this could be treated in a paper which is referenced as subsequent work. And in fact, we have some methods of deciding deadlock freedom of configuration sets. And the problem is, given a formula in separation logic, is there a configuration described by that formula that can lead to a deadlock configuration? And adding error states like these failure states could impact on this deadlock. But this is something we could check in a different way. This is more of a parametric model checking problem than a reconfiguration problem.
Okay. Sophia, hi. You're on the stage.
Hi, thank you. I wanted to go back. Thank you for the answers. I wanted to go back to my question too. You said that you are thinking of making this clustered base reconfiguration program, but I would have thought that once you prove this global reconfiguration program with the technology that you have, there should be another step where you make a distributed version of the program where the various nodes just talk to each other when they decide to do a kind of reconfiguration, and that this distributed version would not need any proof. You just would need to prove the process of distributing, of making the distributed version. Just occurs to me now, it can be totally wrong. So I was wondering what you think about that.
So you mean that we need to have a proof of the clustering, essentially, right? I mean, or if I understand your question,
I would have thought that if a node, for instance, decides to skip its neighbor and go to the next neighbor, then they could start talking to the next neighbor directly and to the neighbor. So it would be like sending messages across those nodes. Essentially what you have described in your paper, but the program that you have shown in the paper, but where you connect and disconnect, these are message sends, and every message has got a lambda of the next message to be executed. So you would create the global program that you have described, you would make a version of it that is a distributed program and is equivalent. So you would only need to prove the original global program.
Yeah, I see a bit of a problem with changing the communication model. Although I'm not saying this shouldn't be done. Probably it should. Our communication model it's just rendezvous with no message passing. In fact, it's just interaction. So just synchronization of local transitions. Once we add messages and message types, then things could change a little bit. Including in the logic and the proof system, and what you're suggesting, if I understand correctly, would be that processes have their own identifiers, and these get sent over, in message passing, and this would require a bit of changes to the behavior model.
Yeah. Essentially, I'm proposing that we turn a sequential program into an asynchronous program. So it requires a lot of thought.
Yes. No, but I see your point, and it's quite good that you bring that up, because our model currently can express it cannot express in general distributed computing. I mean, things like leader election or consensus can probably not be expressed in this model, mainly because of lack of identifiers and messages with data. And adding those, on the other hand, would complicate other things like the logic becoming undecidable and things like that. So, I mean, yeah, there is no free lunch. But we are currently looking at how the behavioral model can be generalized. There are a few works by namely some colleagues of ours from ENS in Paris, and they consider distributed algorithms with identifiers. There are some results about model checking those things, and when model checking problem is decidable and when it's not, and so on. But yeah, I think there are some leads on doing that. I can't say for sure what would it mean for us to change all that.
Okay, and you have another question, Sophia.
Yes.
Can I read? Should I read it, or
go
Sophia?
Ahead, yeah.
I can read it. Thank you. So you showed us these cyclic proofs, and while you were describing that, I thought, is that any different to what we do when we prove we have under assumptions? For instance, when I type check, we don't need to go to the program verification. So if I type check a program that has got mutually recursive functions, what we do is we have a signature for each of the mutually recursive functions, and we prove that each of the bodies, under the assumption of those signatures, has got the bodies satisfy the signature. Or do you need to do these cyclic proofs because you don't know? You are also searching for the signatures while you're proving.
Yes. So in fact, cyclic proofs do not require assumptions. All we need is to have a goal that needs to be proved, and from that goal we apply the proof rules. So we have a proof system with schemes of proof rules, as in virtually any proof system, like in natural deduction or so on. And we apply these rules backwards, and we generate premises, and then we build a tree of premises like that. And the cyclic proofs are interesting because they actually discover these premises that are needed as induction invariants. So they are extremely relevant in the context of induction, when we need to apply some induction principle somewhere. The reason why we need induction is because we have these inductive predicates that are defined like that. So but the reason we used cyclic proofs and not natural deduction was that cyclic proofs are capable of discovering these invariants as we go along. I mean, we just generate the proof. At some point we match something that we have seen before via some substitution, and then we add the backlink, and that ends a branch of the proof. And if we are lucky enough, we manage to end all the branches by either axioms or backlinks, and then we can check its soundness. It was all beautifully summarized in the PhD thesis of James Brotherston in London. I'm not sure it's in UCL right now, but at the time he was in Edinburgh. Anyway, so yeah, this is where cyclic proofs are very well developed and discussed, and the principle they are sound is that you cannot descend infinitely in a well-founded domain, and that's
in a well-founded ordering.
Right. That's